It's another math day here with teacher Jenny. Join me for another topic, and this time we're going to talk about continuity of a function at a number using graphical approach. So let's say we have here a graph and we are going to check whether the graph is continuous at a particular value of x. Say we have here our c equal to -5. So our c, if you try to recall that one under limit discussion, our c is a number in which we are moving our x values towards that particular value. So our c here is -5. So if we are to check our function on this graph, whether this is continuous at c equal to -5, we are going to look at where x is equal to -5 is. This is where our x is as -5, and we are to trace our graph there and check whether our graph has a hole or a break in there. But since here, if you try to look at this, where our c is -5 or our x is -5, we cannot find any hole or break in there. So that means this is continuous at c equal to -5. And what if we have here c equal to 2? We are to check whether the function is still continuous at c equal to 2. So we are to trace again where our c equal to 2 is, or our x equal to 2 is. So this is where our x equal to 2. This one is our c equal to 2. And then we trace the graph again and check whether we have a hole or a break on that particular number. And if you notice, we don't have any break at all or a hole. So that means our function is continuous at c equal to 2. Now let us try to check if the function is still continuous at c equal to -1. So again, our c here is similar to our variable x. We are to locate our x, which is equal to -1, in which it is located here. This is where our -1 is. And if we try to trace the graph, this is where our x equal to -1 is on the graph. Notice there are two endpoints that we are trying to intersect, or is having a value of x, which is -1. First one is this one, which is a shaded one. The other one is a hollow one, or a hole. Now, if you are going to go back, when you say continuous, it must not contain, or it is not with a hole or a break. Now, notice there are two here. There are breaks, or there is a break and a hole. Now, this two situation would really tell us that our function here is discontinuous at c equal to -1, because we have a break. Our graph there breaks at -1. And then we try from here, from this point here, we try to jump over to this particular endpoint so that we can continue our graph to the other side. This one is what we call as a jump or essential discontinuity. This is a type of discontinuity, or once you have your function as discontinuous, identifying this type of situation, this is under the jump or essential discontinuity, because from this point here, might be we are trying to jump over to this particular point so that we can trace our graph continuously. So that is jump or essential discontinuity. Another characteristics for a jump or essential discontinuity is that you will have there an f of c being satisfied, meaning to say you can find an f of -1 in this particular graph, your f of -1 that is equal to a 0. although you've got two endpoints here, but if we try to look at that one, those two endpoints has different characteristics. One is with a shaded endpoint, the other one is a hole. The hole there signifies that we do not include the negative one in our graph on this part here where we have it as blue, marked as blue on the graph. It's not included. The negative 1 as the value of x is not included. While on the red, which is an endpoint which is shaded, this is an indicator that negative 1 is part of our x value on that graph. So, if this is the case that we have here an f of negative 1, which is a 0 here, but then again, the limit from, or f of x from your left side, if you try to look at that, from the left side of negative 1, that is equal to, this is 1, this is 2, so our limit there is equal to 2. And our limit of f of x as your x approaches negative 1 coming from the right side, which is this graph here. Once we move closer to the negative 1 there, our limit becomes a 0. Notice that the limits on the left and right are not equal, so our limit here does not exist. That is, the limit of f of x as your x approaches to negative 1 does not exist. That's a DNE. So which means, once you've got there a jump or essential discontinuity, yes, we have an f of c value there, but on the limit, we don't have a limit because the limit does not exist. Now, let's now move to this example, this graph. So, is the function continuous at c equal to 3? Now, if you again trace or locate x equal to 3, this is where our x, which is equal to 3, is. Tracing the graph there, you would notice that once we are tracing the graph, we have our point here, which got an x equal to 3 as this one here, which is not a hole, which is not a break. So that means our function there is continuous at c equal to 3. So let's have our, let's try to check our function whether it's continuous at c equal to 4. So again, we try to trace where x is equal to 4. So we have this as our x equal to 4. Tracing our graph here, you would notice that the graph there, as your x equal to 4 is, we've got a hole. This would signify that our function there is discontinuous at c equal to 4. And this is what we call as the hole or removable discontinuity. Hole meaning we have here a hole which will serve as the breaking point of our graph. That means it's not continuous anymore at this particular value of your x. Now, characteristics of your hole or removable discontinuity is that we do not have an f of c. Our f of c there does not exist. So if you try to look at that, your f of 4 is not existing because 4 here has a hole on that graph, meaning we do not include 4 on that particular graph as your x value. So our f of 4 is DNE. Now, since your f of c is not existing anymore, automatic, we do not go for testing our limit therein. Although, if you try to really wanted to go for a test on the limit, you will notice that we have the same limit from the left side. So if you try to look at the graph, from the left side of 4, this is where our direction of the graph is, moving towards 4 coming from the left, you would see a value of your y, which is 7. And if you try to move closer to your 4 coming from the right side, this will also be obtaining the same value, or we are moving closely to the same value of our y, which is the number 7. So meaning, for a whole or removable, we don't have an f of c, but our limit there exists, which is this example, we have our limit as 7. So that is the characteristics of a whole or removable discontinuity. So let's go for another example. So this one is another graph. So if is the function continuous at c equal to 0? So again, we try to trace where x is equal to 0 here. This is where our x equal to 0. Tracing the graph, we can really see that the graph there doesn't contain any break or hole. So that means to say that this is continuous at c equal to 0. Let's try to move for another one. Let's say we have here c equal to -1. We're trying to test whether it's continuous still on that particular value, which is -1. Again, locating x equal to -1. This is -1 is. And if you've noticed, we try to trace the graph. Notice that the graph there is moving closer to the -1 from the left and the right, which means our -1 there is our asymptote. Again, this one is an asymptote, meaning we move closer to that particular value of x, but your graph will never be touching that one nor crossing that particular value of x. So that's an asymptote. Now, once you've got an asymptote, automatic, although this would somehow satisfy that our limit are the same, we've got there a positive infinity, because although this one is not containing an arrow there, but this really moves up continuously, indefinitely. So if you try to figure it out, you would notice that we have there a limit which is a positive infinity. But then again, if we try to look for our f of c there is non-existent, meaning it does not exist. F of -1 do not exist because we don't have a point on the graph there. So since that is not existing, automatic, why go through with the hassle of going through with the second condition, in which testing out whether they have the same limit on that particular function? That doesn't make sense because, again, f of c is not existing. So this one is what we call as an infinite or asymptotic discontinuity of a function, because again, we are trying to move, our graph there is moving towards an infinite direction. May it be with the same direction infinitely, may it be positive infinite, negative infinite, or with different infinity in there. That is an infinite or asymptotic discontinuity. It will never be continuous because the graph there breaks at a particular point. So this is how you view continuity of a function using the graphical approach. Once again, this is your teacher Jenny saying practice and practice, and that will make you perfect someday.